Hi, everybody. Thanks for coming along. This is not only for these who are here right now, but for the multitudes who will later be watching this on YouTube. So my name is Dan Suttin. In the chat box, it says Kevin Rayhans, but that's me, Dan Suttin. And Kevin is the technical person here at San Antonio College, where I work as a math tutor. And he has been kind enough to set up this equipment so we can do this. So, though I'm a math tutor, my real passion has to do with polyhedron models and OCTATETRA constructions, as they call them. And I'm going to take you along on an adventure with me today. So, my first question, you see the little question mark on the screen there, is who can identify what that is a picture of? If you know, just type it in. Let's see if anybody knows. It's from 1960. JD recognizes it as the time machine. So we have to see the backstory, and we're going to go back in time. So we're just going to pull back on the lever, and the wheel's going to start to spin. And we're going back to 1979 when I found this book on the shelf in the library, Polyhedron Models by Magnus Wenninger. I did not have any idea what a polyhedron was. I knew what a polygon was. Let's see if you can see these. This, of course, is a polygon. It's usually called a triangle, of course. I like to call it a trigon because that's more of a polygon-sounding thing. This, of course, is a square. I like to call it a tetragon. And here we have a pentagon and a hexagon and an octagon. Everybody knows these. We learn about these in the 6th or 7th grade. But they never seem to teach us anything about what a polyhedron is. So a polygon has many sides, and a polyhedron has many faces. And I'm wondering if there's ways that we can put these faces together and build something that's three-dimensional. And my next question for everybody, let's see if there's a little question mark there. There's supposed to be. It'll come up. Okay, here's the guy that wrote the book. His name is Magnus Wenninger. Look at those beautiful models he made. This picture is about 10 years ago when he was in his 80s. He is now 92 years old. And I'm going to read you this little quote from his book. It says, "It's really surprising how much enlightenment will come following the construction of the models rather than preceding it. And once you begin making them, you may find that your enthusiasm will grow. You will soon see that each of these solids has a beauty of form that appeals to the eye in much the same way that the abstract mathematics appeals to the mind of the mathematician. It's one thing just to see a picture of them. It's another thing to hold it in your hands, and you get in even more deeply if you actually build it and see the pieces coming together." So the question is, how many ways are there that these polygons I showed you can be made into some sort of solid? But it has to be a uniform convex solid. Here's an example of one that is not. You see it's got some places that are cavities that are concave, and it's not uniform at all. So it has to be approaching roundness, at least uniform on all sides. And it can't have any cavities. So take a guess. Is it 5? Is it 10? Is it 20? Is it 50? Is it 100? Is it hundreds? Let's see some guesses in the chat box there. How many ways can we put these polygons together to make a polyhedron? No guesses yet. Is it 5, 10, 20, 50, 100, hundreds, thousands? No guesses. Are they talking it over there in Greg's group? John Oakes is typing. He says, infinitely many. Well, there are infinitely many ways that you can use these equilateral triangles, but not if you want something that's uniform and convex. This thing here that's just made of triangles is just called a deltahedron. It's kind of a general term. Well, I will tell you, Going once, going twice. There are exactly 18 ways. The first 5 are called the Platonic solids. The tetrahedron and the octahedron and the icosahedron are all made out of just triangles. So this little baby here is the tetrahedron. And then, which has 4 triangles, 4 faces. This one is an octahedron. It has 8 faces. Each of these has the same side on its polygonal sides. Everybody knows that's a cube. Okay, that has 6 squares. Now here's the icosahedron. I had never heard of this when I got that book. And I was an educated fellow. I went to a really good high school. I went to a college. I was teaching in a school, and I'd never seen this in my life. Then we have a dodecahedron. This is made out of 12 pentagons. Now, we'll go down a little bit. It says that little square there says I should show you something. I need those 5, in the first 5 in the front, coming in order. If we take our tetrahedron and we truncate it so that good, I'm glad you supersized me. We truncate it, so we cut off a corner, we have the truncated tetrahedron. If we truncate the octahedron, we get this one. That's an octahedron with the little corners cut off there. If we get a cube and we truncate it in just the right way so the length of the sides, I guess I have to show on the other side there, the length of this edge is the same as the length of this edge. So this is the truncated cube. And if we truncate the icosahedron, we get this. They're getting bigger and bigger. This one looks like everybody's soccer ball. Most soccer balls are made in this format. Yes, these can all go away. And finally, we have the truncated dodecahedron. So far, we've seen 10 of them. These can just go anywhere. I won't be using them again at all. Okay, let's go back. Downsize me, John. Okay, and we're going to go down there. We see the 5 Platonic solids, and we see the beginning of the 13 Archimedean solids. You just saw the truncated versions. Now we have another family coming up. I need the 1st and the 4th. Okay, this one is called a Cuboctahedron. What you're having here is Polyhedron Models 101, just a little survey. It's just an intro to where we're going. Okay, this one is made of the 6 squares that you find in the cube and the 8 triangles that you find in the octahedron. Every square is surrounded by triangles. Every triangle is surrounded by squares. It's the Cuboctahedron. If we do the same thing with pentagons and triangles, we get a combination of the icosahedron and the dodecahedron. It's called the icosahedron. They have great names. Okay, I need next, not that. Yes, that and, well, if we take the Cuboctahedron and we add some extra squares to it, we get the rhombi Cuboctahedron. The rhombi Cuboctahedron. And if we take the icosahedron and we add some extra squares in that, we get the rhombi icosahedron. This is my favorite. I think this is the prettiest one. So these 2 families are related. These 2 are related, the Cuboctahedron and the icosahedron, and then we truncated each of them, and we got something new. And then we got, if we take the rhombi, I'm going to need this one again. If we take the rhombi Cuboctahedron and we truncate that, we get the rhombi truncated Cuboctahedron. And if we take the rhombi icosahedron and we truncate that, we get this one. It's the biggest one. I have to lean back to get it all in. The rhombi truncated icosahedron. So we had 5, and then we had 10. That's 15. Okay, I need this, but these guys can go. I'm going to need one, again, that looked like this. Right in front of you. I'm just going to need it there on the table. Okay, so we've seen the 10, and then we just saw 6, so we're up to 16, actually. So we just saw those two families there. And now we have this guy. Okay, you can supersize me again. Okay. And I made 2 of them. The question is going to be, why did I make 2 of them? This is called the Snub Cube. The snub has something to do with it. There's a little twist in it. But each square is surrounded by a ring of triangles. Each square. Then if we take another one, we have the snub dodecahedron. Each pentagon is surrounded by a ring of triangles. But the question is, and this is a question for everybody to consider, and I'm hoping someone will type something in the box. Why did I make 2 of these? Okay, you can downsize me. Let's see if anybody has anything to say about that. Why did I make 2 of them? Nobody has a clue. There's an answer. John Oakes is typing. What is John Oakes thinking? Anyone have any suggestions? That's my question too. Anybody have any suggestions? We'll scroll down a little bit and you'll see the ones we just talked about. And here's 2 of them clearly shown, and the question mark is there. Why did I make 2 of them? I will give you a hint. Going once, going twice. Hint. That's my hint. Why did I make 2 of them? Any ideas? Are these 2 the same? Or are they different? Well, I got the left hand and right hand. These 2 things have the quality called chirality, which translates as handedness. So they are mirror images of each other. The fancy chemical name for that is enantiomorph. All right, let's see where we go from here. So those are the basic polyhedra, all 18 of them. Even though I made 2 of the snub cube, it only counts as 1. So here's a picture of what you just saw. And then we have the stars. I'll show you these very quickly. These are stellated versions. You can supersize me so they can see them. These are stellations or star forms of the dodecahedron. This is the first one. This one is considered the second one. And this one is considered the third one. And this is the one that's on the cover of Magnus's book. Okay, we don't need those anymore. This can go any old where. And then we'll scroll. Well, here's another one. This one is a stellation of the icosahedron. Notice that when you see it in that view, you see the 5-pointed star or pentagram. Depends how I tilt it. Ooh, it's hard to figure how to tilt it with. You see the 5-pointed star, but then if we tilt it the other way, you kind of see more of the triangle. So that was a really fun one to build. And the last one is called the compound of 5 tetrahedra. There's 5 of them in there, 5 different colors. And this thing happens to fit inside of a dodecahedron, which is the thing made out of 12 pentagons. Okay, downsize me. So, back in 1979, are we scrolling? Yes. Back in 1979, I discovered this book in the summer, and I made a set of all these models, and I brought it into my classroom. I was teaching a group of kids at the Cambridge Montessori School in Cambridge, Massachusetts. They were from 10 years old to 14 years old. And I had each of the kids make the first 5 that were easy, and then depending upon who was really good at it, the ones that were really good got to make the really hard ones, and the ones that had some trouble with it got to make some of the easier ones of the other of the 18. So we're scrolling down past things that you saw. And we're ready for what's next. It says I need to show you something. Okay, I'm going to make this little table in front of me here, because since every kid in the class had made the first 5, we had this. We had a whole bunch of them. Now we need to tilt that forward. Okay, so these are just lying here on the table, and we made a discovery. We found out that we could put them together. The purple ones are the Tetrahedra, and the orange ones are the Octahedra. And we found that if we alternate the colors, we can build stuff out of them. And we were excited. I'll tell you, it didn't say anything about this in Magnus Wenninger's book. And it was 1979, and there was no Google and no internet. And I thought, oh my gosh, maybe I've discovered something that nobody had discovered before. So I was super excited. Notice that we've made a tetrahedron that's 3 units long. Let's see if I can grab this. Over here, I'm just going to dump that back. You can see over here, here's one put together with paper clips that's 2 units long. So we're going to put these guys back in their little basket. Then, a little while after that, we made another discovery that at the time I was rather startled to make, because I've been playing with them, and it hadn't occurred to me what you're about to see. Here's a nice beam that you can make, so you can construct something really big. As a matter of fact, if you make a beam like that, hand me that guy back there. Here is a larger tetrahedron. It is big, isn't it? Okay, let's go back a ways so they can see it. There we go, there we go. Okay, this was made by a group of students at a little school here in San Antonio called the Guardian Angel Performance Academy. This was a group project. Okay, so you can have that back. So we had these lying on the table, and then I made this discovery, that I could turn this, lift it like that, and fit that in like that. And I could fit the other one like that, and suddenly we have something that has a square in it. Okay, take all that. Then, if I've built that, if I put this in here, and I put another octa in the bottom, I've made an octahedron that's 2 units long. So, I was pretty excited about that. So, I'm done with that. Okay, downsize me. There, I'm back. Okay. So, I thought that I had discovered this all by my little old self, but I discovered finally when the internet came in and I could do some Googling that a man named Buckminster Fuller had a patent on that. Hand me that little guy right there with the 2 colors on it. He had patented this construction as something for a structural system. Okay, so here's what he patented. It's exactly the same thing, if I turn it the right way, as what is on there. Okay, so that was in 1961. We're going back further and further in a time machine. Here are the things that I showed you already. And that's part of his patent. Then it turns out that in 1959, an artist named Moritz Escher, M.C. Escher, made a drawing that had lots of different OCTATETRA configurations in them. And I have made all of them. They're really very interesting. There's lots of stuff going on in that picture. Then we go back, surprisingly enough, to Alexander Graham Bell, who invented the telephone. And after he invented the telephone, he wanted to invent the airplane. And he was going at it from the point of view of building kites. And this is an OCTATETRA kite. Then we go back all the way. Well, here's another. This is 2 of his assistants carrying one of his OCTATETRA system kites. Then we go back all the way to 1568 to find this drawing, which has tetras and octas in it. It also has something that some of you may know about called a Sierpinski tetrahedron, who was the guy in about 1900 that was interested in fractals. Now we go back to this drawing. I will tell you that this drawing was made in 1497 by a very famous artist. Anybody want to venture a guess as to who this very famous artist might be? Let's see if anybody types something. This is in the Renaissance. The drawing was made in 1497. That's 5 years after Columbus sailed the ocean blue. Greg is typing. And it was done by an Italian in the Renaissance, Mr. Renaissance himself. Today, a Renaissance man is a person who is well-versed in many fields. Yes, it is Da Vinci. Okay, his first guess was Dora, who did some really neat things too. It's Leonardo da Vinci. Now, Leonardo da Vinci, and because of that style of drawing, that style is called being drawn in the Leonardo style with the spaces in between. And you can see that my little octas and tetras are all done in the Leonardo style. Okay, now Leonardo had a friend, and his name was Luca Pacioli. They were buddies. Luca Pacioli was a mathematician, and he was writing a book about math. The name of his book was De Divina Proportione. The drawing was made in 1497. The book was published in 1509, and they called it a raised octahedron, which shows that they knew that inside all those tetrahedrons there was an octahedron. But there's really no evidence that they knew, let's supersize me for a moment, that they could put another octa in there and make a building beam like this. So that is really the end of the line as far back as we can go, though I will show you some more fringy kind of things that may show some evidence that people knew about octas and tetras fit together. So here is a page from Pacioli's book. Those drawings are by Leonardo da Vinci. There are actually only 2 copies of this printed book. The word they use is extant, E-X-T-A-N-T, which means that exist at this time. One is in Milano in Italy, and I think the other's in Venice, or somewhere close to Venice. Now, let's see what we have. Okay, here's something. Here's 2 more pictures from that book. There was some that I wanted to still have here that I had you take away. It's the one, there's 2 of them there, right next to the big one. Yes, exactly those 2. Okay, this one here is the, it's this one. It's the Cuboctahedron. I don't know which, every time I go down, it goes up. I have to get used to this. This is the rhombi Cuboctahedron. But here is another one. Okay, I have to move back a little bit. Okay, why did I make 2 of these? Can anybody see any difference? You can, up is down, down is up. Okay, can anybody, you can downsize me again. Can anybody give me any suggestions as to why I might have made 2 of these? They are different. There was a guy named Miller in 1930 that was trying to build this one, the rhombi Cuboctahedron. But he made a mistake when he built it, and he got something else. Can anybody see how it's different? Any ideas? No ideas yet. Going once, going twice. The bottom third of this one has a little twist in it. It's twisted. So when Mr. Miller built it, he attached the triangle to the wrong piece, and he got that. This one is called the pseudo-rhombi Cuboctahedron. And because of this, they had to make the definition of what a real uniform polyhedra is, a uniform convex polyhedron. They had changed the definition to disqualify this new one. So that was 1930, and everybody has thought for many, many years that that's as far back as that goes. But these two pictures you see here were in an article in the Scientific American about 2 years ago, and the guy who wrote the article said Leonardo da Vinci made a mistake in this drawing over here, the one with the more complicated one. It's a rhombic cuboctahedron, but it's got a square pyramid, which is half an octa on each square face, and it's got a tetra on every triangular face. But the one on the bottom is the wrong one. So this guy was all excited that Leonardo da Vinci had made a mistake, and nobody had discovered it in this diagram, in this drawing, for all these hundreds of years. So if my friend sent me that, and I sent that to all my polyhedron friends in an email group, several email groups that I belong to, and they had this big discussion, and they came up with the conclusion that it's not that Leonardo made a mistake, is that Leonardo had discovered what this guy Miller had discovered in 1930. He had discovered it in 1497. So that's the real significance of that drawing, and that was a pretty cool discovery. Here's a picture of it, and you can see that if you twist the bottom, you get the other one. It's a little bit twisted. Now, one of the fellows who was in the discussion was Carlos Sequin, who's a professor in the Math and Computer Science Department at Berkeley. And I sent him some of my OCTATETRA pieces that I crank out on my little machine, and he went ahead and he made the normal one and the twisted one. And it was actually a very difficult model, so he's one of the few people in the world that has done any models with my pieces of that degree of difficulty. Now, I showed these pictures, this whole presentation, to my grandson, who is 12 years old, and he said to me, "That's like a Rubiks Cube." And I said, "Wow, I never thought of that." So I Googled Cuboctahedron and Rubik, and I came up with that. They actually have Rubik's things that are in the shape of a cuboctahedron. So I learned something brand new just because of this little comment that my grandson said. Okay, now it says I'm supposed to show you something. Yes, I think I know what it is. I don't want to go any further than that. Okay. You can supersize me. I found out along the way, and I was very disappointed, that 5 octas will not fit together. You can see there's a gap here, over here, of about 7 degrees, which meant I couldn't make any of these structures or things like the pentagonal polyhedrons, that it didn't work. I was very disappointed, and I put this project aside for years and years and years. But then the internet came in, and I found a guy named George Hart, H-A-R-T. If you go to georgehart.com, you will find the most wonderful website about polyhedra. And he said to me, you know, if you shorten these sides here just a little bit, and he had some trigonometry in his message, which I've long lost, unfortunately. But the bottom line is, if you take about 2% off so that it turns out to be an isosceles triangle, you can get the gap to close. And then if you do that, you can make things with pentagons in them like this big one that I'm about to show you. It's so big that I'm going back and back and back. Okay, here it is. This one's called the little soccer ball. It's made just out of that little ring of 5 octas that have the little adjusted pieces, and just tetras. So those are the modules. The thing about building with OCTATETRA is that you get a module that you repeat over and over again, and you wind something. So here it is on the outside, but I didn't want to close it up because I wanted people to be able to see how cool it looks on the inside. So we're done with that one. So I was able to make models like that, and then you can keep me supersized because I have another one to show. This is a larger ring. Now, in order to make this one side of the octaves is a little darker color. You can't tell at all from where you're looking. But one side has something that's a little longer, because if you make the inside one a little shorter, you have to compensate for that to make the outside one a little longer. And it does work that tetras can fit in here. You can put two tetras in there on one side. See how I put that in there? But you can't do it on the other side. And you also can't make a ring any bigger than this. But I've made some really nice models with this as a module. I've made some bigger soccer balls instead of little ones. Okay. Now, let's go down to the next page. Downsize, please. As we go down, we see a pentagon. Now, I often introduce this by telling my students about a circle. I say if you have a circle and you measure the circumference with a tape measure, and then you measure the diameter, and you take the measure of the circumference and you divide it by the diameter, you get this special number that every 7th and 8th grader knows about. So somebody in my audience should be able to tell me what that number is. What could that number be? Chance to type something. Nobody's typing. Somebody's typing. John is typing. John knew it was pi. Okay, it so happens if you take a diagonal of a pentagon and you divide it by the side, you get a very special ratio called the golden ratio, which appears all over the place in mathematics and all over the place in nature and in things that grow. It's also called the divine proportion, which was the name of Posseoles Book, Leonardo's friend. So I have another email friend named Sandor Kabai from Hungary, and he taught me a little more about that. But first, you see, Luca Pacioli defines the golden ratio as the divine proportion. It means that you can take a line and divide it in two pieces so that the ratio of the whole thing, A plus B, to the blue piece, A, is the same as the ratio as A is to the little tiny piece of the line. Now, we also see a pentagon there with lots more diagonals. If the side is 1, the diagonal is the golden ratio number, which is 1.6 something something something, and that's depicted by the Greek letter phi or phi. But if you get two diagonals to cross each other, that diagonal is divided into golden ratio numbers. So one of them is 1 over phi. If you play with that equation and you use the quadratic formula on it, you'll see I've done that there on the side, you'll find out that the number we want is 1 plus the square root of 5 over 2, which turns out to be that 1.6. So my friend Sandor Kabai sent me this little diagram, and he says, why don't you make your pieces like that? You'll see that there's a 1 over phi involved in that. The golden ratio is involved. Before, I was making my little guy. Where's my little guy? I don't have him anymore. This guy, okay. I was making the center pieces short by about 2%. This is actually a little bit shorter. These pieces on the side, these blue edges there, by about 5%. My pieces are 100 millimeters, and that special side is 95.1. So I began to crank some of them out on my little machine, and I made what he called, Sandor Kabai calls, the golden octet truss. And whereas the other things I was making with pentagons was kind of cheating, this is not cheating. This fits together exactly. And it says I'm supposed to show you something. I'm supposed to show you that big thing over there, the big green one. And you'll notice that this one goes out another layer. Oh, there it is. This is the golden octet truss, and it involves the golden ratio, and I'm hiding behind it. And you can even have stuff on the inside. Everything fits together perfectly. This poor thing was damaged from its last outing, so it's crinkling and crushing even as I hold it. Okay, we're done with that. Okay, moving right down, please. Downsize me. Looking for downsize. There we go. And we go down a little further. Now, before Leonardo da Vinci, I read a paper called Cuboctahedron Revisited. This little thing at the top of the column is our Cuboctahedron. And this comes from a building in Turkey from the 1300s. That's 100 years before Leonardo da Vinci. But there's no evidence that they knew that inside the Cuboctahedron was octas and half octas and tetras, like the little model I made there. But in this paper, they talk about some other things that are related. This word vector equilibrium is Buckminster Fuller's fancy name for the Cuboctahedron. And when you have a whole construction of it, it's called the isotropic vector matrix. And that has something to do with something called the flower of life and the tree of life. But when we start talking about those, we're getting into fringy stuff called sacred geometry. And one guy who gets really deep into that stuff is a guy named Nassim Haramein, who has some very interesting YouTube videos. But he's called a pseudoscientist, and not many people take him seriously. And one of the reasons they don't take him seriously is because by the end of his presentation, he's talking about how the pyramids were not made by the Egyptians, but were made by extraterrestrials who came to Earth. So he reminds me of my two favorite fictional scientific characters from movies and television. One of them is Dr. Daniel Jackson, PhD, well-educated, and the other is Dr. Ellie Arroway. Can anybody identify those characters? Dr. Daniel Jackson and Dr. Ellie Arroway. Both of them believed that there was some kind of contact with extraterrestrials. Virginia Anson is typing. Stargate, absolutely. That's Dr. Daniel Jackson. Here he is from the movie. Okay, now how about Dr. Ellie Arroway? Okay, John is typing. John knows this one. He says, he's typing. Boy, he's typing a lot. Great job, Virginia. Do you know this one too? Okay, no answer yet. Who is Dr. Ellie Arroway? Something about contact with extraterrestrials. Going once. Oh, I'll show you her picture. There she is. Anybody recognize that? Jodie Foster. What's the movie? Going once. Nobody's typing. Going twice. JD says Contact. I hinted when I said Contact. Okay, that's the name of the movie. You got it. So those are my two favorite fictional scientists. Now, here's something that I built out of my OCTATETRA pieces. These are all made out of normal pieces with equilateral triangles. So the pentagons didn't really meet. They had to be forced. But this is here at San Antonio College. This piece was up for 14 months. It has 3,600 pieces. It has glue, but it also had 55,000 paper clips. And there's a picture of me standing there in the middle of it and another picture of it with students walking through the hallways and looking at it. And one day after 14 months, it crashed. It was under a lot of strain because it was a sheet and it had to be forced together. And those 55,000 paper clips were pretty weighty. And I think maybe it got bumped a few times on those sticks that held it up. Anyway, down it came. I didn't have the heart to try and rebuild it, so I just told them to put it away in the garbage. But that was a good adventure. But I wasn't that upset because I was already working on a new project called the OCTATETRA Museum. There's I am standing outside of it. It's in a warehouse here in San Antonio. Mission statement says to inspire future architects, engineers, designers, artists, and mathematicians to pursue educations and careers in those fields. To advance the understanding that the above-named fields of endeavor are not mutually exclusive, but that they overlap significantly, and to celebrate creativity in all of the arts, which means I can put anything in there that I feel like. And here is the Mega Tetra, the one behind. That took me 2.5 years to build. It has 26,000 pieces. And the one in front of it is the Mini-Me Mega Tetra. And I'm going to show you where that comes from. First, just hand me the bottom ring. Okay. All right, we'll take the whole thing. Here we go. So, I showed you how 5 octaves do not fit together to make a ring, but I discovered all on my own, of course not the first person to ever discover it, that you can put 12 of them together to get a ring. So we put that like that. We're going to need to tilt the camera. Then you can build up on that. You have to go a little bit forward there. Very good. Okay, and I can go back if I have to. Very good. Okay. And you can see there's a ring on each side. It's got 4 rings. It's in the overall shape of a tetrahedron. If you continue this on and on and on, you get something called a diamond lattice. I also found out that if you put these guys on the inside and then you cover that up like that, you can feel that there's a roundness here of some kind of ball. If I continue that roundness on the outside, I will have a complete circular spherical cell that's called a rhombic dodecahedron. Now, you can downsize me. Downsize me again. The little guy in the front is the diamond lattice made just out of octahedra, and the white ones are the 3 rhombic dodecahedral cells at each corner. But I decided I wanted to make, instead of just octahedra, I wanted to make it more interesting. So I devised 3 different modules that have the same face angles. The little yellow-orange one in the middle is just an octahedron with 2 units long. The thing on the bottom is a truncated stella octangula. It's this guy here, but with the tips cut off. And the top one is a truncated tetrahedron, which is one of the ones we've seen. So when I put all that together, I got the big mega tetra. Here's how it looks if you look through it. There's all kinds of cool tunnels in it. And I think I have a picture maybe of another tunnel. This is the tunnel through the rhombic dodecahedral. This is a little rhombus shape in there. And we move along and we see in my museum, we have pictures of other modules that you've seen. I've got my Einstein Imagination is More Important Than Knowledge t-shirt on. Here we have Stepping Back. You get to see what the place looked like. This was on opening day. Actually, it's much more crowded now. It's been up for a year, and I put tons more stuff in there. The most important thing about my museum is the people that go there, especially the kids. I made it for the kids. This is a group that came from something called Inner City Development in July. On every Friday, I had a group in the morning and a group in the afternoon. They came in and I taught them how to put the pieces together with the paper clips. It takes a group that size about 40 minutes to learn how to do that, because there's an absolute right way and a whole bunch of wrong ways to do it. Here's a group from the Southwest School of Art. They came to the museum, then we went back to the school, and as a group project, they built that in 5 mornings. And these kids are young. Most of them were 9 years old. So they didn't have the skill to do it with paper clips. They did it with Scotch tape. So it's a little flimsy, but you have to be 10 or 11, 12 years old to have the ability, the fine motor skill to be able to handle paper clips that well. Here's the thing that they built back at the museum. Here's a part of my museum with pictures. I call this the Great Wall, pictures of a lot of the models I built. And here's a table called the tutor's table. And I let people know that any student that comes to my museum, if they come make an appointment and come at a time when I'm not super busy showing things to other people. I will sit down with them and help them with their math homework, free of charge. And I've had some takers on that. Everything from basic mathematics all the way through college algebra and pre-calculus. This section is called the reading room, and you see there's some volumes there. I have over 500 files that I put together on the stuff that I've built, plus all kinds of cool stuff in art, architecture, engineering, design, and mathematics. Now, this OCTATETRA construction is also used in the real world. This is a library, the San Antonio Public Library, a branch of it, on the north side of San Antonio under construction. The entire roof is OCTATETRA. And what do I need to show them? Here, it's right here. Okay, supersize me. This is made of half octas and tetras. But you see how flimsy it is because the octaves aren't complete. But if you attach it to a ceiling like that, it's very strong and rigid. So that's what they do with most of the buildings that use OCTATETRA out there in the real world. This one is at Six Flags, Fiesta, Texas. It's a ride called the Tornado. I recently did a presentation similar to the one you're seeing, but for 7th and 8th graders, a live show. And all the kids in the audience knew that place because they'd been there. They'd been on that ride. And if you look at it close up, you see that you have half octas and tetras in that structure that holds that thing together. This is a building in San Diego, California. I first found it on a geometry book from a guy that I was tutoring, and then I Googled it online, and there it was. It's a complete OCTATETRA half octa square base pyramid. The second picture, I put a little picture of my model of it in the corner there. Then finally, I just want to show you one more project that I worked on. It was called What's Next, because it's the next thing I did after I did the Megatetra. What you're seeing is half of it. It's made out of 1/16 by 1/16 balsa wood sticks. There's a picture of me working on it. Very, very delicate work. And then I had to make the other half, and then I actually got it to hang in space. Now, the way it hangs, it looks very chaotic, but it's extremely ordered. And there's a little description there. I'll just read it to you, if I can even see it. It says, begin with a green section, which I call a seed. Programmed into its DNA are instructions to grow black sections or branches 2 units in one direction and 3 in the other. And then to end with a purple section, which is called a flower. That's the ending, forming a ring that doesn't quite close. Well, then I grow out of that ring in the other direction, and then I look around in space and I find another ring that's a mirror image of it, and they join and they dock at the blue one. And the blue one sends out a little shooter 3 units long, and the pair of them looks for another pair of rings, and they dock up, and then we have a foursome. And that foursome looks around in space until it finds another one, and they dock finally at the red one, which I call a stopper. That's the end of the line. So it's 8 rings all joined together. It looks confusing, but there's chemical compounds that in 2 dimensions have orders that are structures that are very ordered looking, but when you see them in 3 dimensions, they're very chaotic looking, although highly ordered. And that, my dear friends, brings us to the end of our presentation, except supersize me, John. I want everybody to see this. Okay, not only is that, did I hold it right side up? Yes, and he made it cleaner and clearer. This is my email address. You can email me and we can stay in touch. You can, I will even email you this file that you saw if you'd like to have it. Just ask me for the file from the webinar, all those pictures you saw, or any other file. I've got over 500 of them. And we can keep in touch. And I'm doing this mainly for the people out there in cyberspace who watch this on YouTube, because they need to know how to find me. And now we're ready for questions and answers in the official 5 minutes that we have left. So, anything you'd like to say, anything you'd like to ask? I hope
yes.
you enjoyed
Does
it.
anyone have a question for Dan?
Anybody typing? Anybody thinking? Did anybody think it was cool? Okay, JD says, multiple attendees are typing. That's what I love. Multiple attendees. Greg is typing. Kristen, way cool. Okay. Are any of the people in Greg's group, are any of them young people? Are any of them kids? Are they all college teachers? The question, of course, comes up of what value is this to a college teacher who's teaching college algebra, trigonometry, calculus. I asked that question myself. I asked it of my polyhedronist friends to see what they would think, if they could give me any advice of how I should spin this to make it attractive to college teachers in the two-year colleges. And Magnus Wenninger, the guy who wrote the book, okay, we got people here. How often do you just play around with shapes, and how often do you make precise calculations first and then build? I never make precise calculations first. I just play with my shapes and make modules. Hopefully some of you have seen the Flickr photo stream of some of my models that's in the introduction. When you go to the AMATYC site, there's a bunch of links there. There's a link to my museum, and there's a link to my photo stream. You see some of the different models that I've made. I never do any calculations. I just devise modules, and then I play with the modules to see how they fit together. It's all discovery. The group here in Athens is all adults. Okay. So I asked Magnus Wenninger, and he said, I feel you need no other advice for your upcoming presentation than simply this: go ahead and do it. So that was encouraging. Then I asked George Hartwood, who was the guy who told me that I should shorten the lengths of my triangle so I could make the pentagonal structures. And he said, math teachers are interested in many topics. And then he said, they're often tired of the topics they have to teach. So I expect you'd be interested, they would be interested if you promote it as having general mathematical interest and say it suggests projects that would get students engaged in mathematical thinking. Okay, Guy Inchbold, who was a total expert in this stuff from England, he said, if it were me, I'd focus on making a great presentation, let them worry about the teaching side of things. Kirby Erner, who was a world-class geodesic dome kind of guy and an educator, says, your museum is a great lightning rod in that it gives specific and tangible form to where STEM is already taking us. Ah, Virginia says, my audio is breaking up. I would like the links. Thank you. Okay, either John will send them to you or you can email me at that address that I showed. I will show it again in case you didn't get it. And it's also in the preview that you saw when you saw this advertised in AMATYC. So you can email me. Is it upside down or right side up? It's upside down. You want to supersize it just for a moment, or is it too late? There it is, super duper supersized. Uncle Dan at homespunforhomeschoolers.com.
Well, let's.
Okay.
Well, I just want to make sure that the people who only can stay an hour get to hear about our survey. And so, if you don't mind, I just want to thank everyone for attending today, and thank you, Dan, again for presenting to us. And remember that you can like AMATYC on Facebook at facebook.com/AMATYC, and remember that, again, recordings of this and other past webinars can be found at bit.ly/AMATYC webinars. And if you could please take 2 minutes today to fill out the evaluation of today's webinar, this will be valuable information to us and to the presenter today, Dan, and that's at bit.ly/AMATYC102. And if you need the email confirmation for your participation in this webinar, just fill out your contact information in the optional section at the end of the survey, and we'll make sure that you get the certificate email or sent to you and whoever else at your college may need it. And that's all that we have today, and if you want to stay to ask Dan additional questions, you are more than welcome to. So are there any other questions or comments for Dan today?
Okay, thank you for those comments. Greg, I would love to have you connect with me if you ever come to San Antone. Indeed.
Yes, but it looks like people are slowly trickling out, so...
out the exits. All right, I had fun, everybody. I hope you liked it. I had a lot of fun doing this.
Yes, well, thank you again, Dan, and I'm going to stop the recording right now.
To get this together.
So I did